Hi, I'm Kavya, and this is Lab 3 for Physics, which focuses on black holes. So the purpose of this lab is to determine the mass of the black hole and find the initial velocity the ship has when it leaves the planet in order to fly in space without crashing into the black hole. This experiment uses the fundamental principles of Newton's second law and the universal law of gravitation and helps deepen the understanding of those concepts throughout the experiment. The results, which we'll get into more detail later. So, the fundamental concepts are gravitation, which is the mutual attraction between all the masses in the universe. This is present in the lab due to the attraction between the planet, spaceship, and black hole. We also use Newton's second law, which are the forces acting on the object in the space are very relevant to this lab. We have to consider both the perpendicular and parallel forces on the objects we're analyzing. So the equations we're using is that the magnitude of the force of gravity is the gravitational constant times both the masses over r squared. And then for Newton's second law, we have F net equals dp dt, which can be derived as F net equals d over dt, and then the magnitude of p and the direction of p, so p hat. And then we need to consider both the perpendicular and parallel forces in order to find F net. We also use the position and velocity update formulas. So in the experiment, the forces are the gravity of the black hole in the star and the gravity of the black hole and the planet on the spaceship. And then we also have conditions. The main result is that the lab showed the mass of the black hole, which we then used to find the initial velocity needed to not get stuck in the black hole. So the procedure is to use a starter code given to you as a starting point, then manipulate the code, which I'll show later, to allow you to find the mass of the black hole. Then taking that mass, we plug it into the second starter code, and then we can find the initial velocity and guess and check what velocity works. So to find the black hole mass, we put in my email to get specialized values. And then, as you can see, we have to go over here and change the P initial, P final, delta V delta P, and then dP dt. So on the right side is essentially all the code that we switched in order to manipulate the code to get the mass. And then we have the resulting picture, which shows the planet orbiting around the black hole. And it's given that our mass is 1.4 e to the 34. And then to find the initial velocity, we take that mass and plug it into our code for the black hole mass, which you can see on the top left. And then we have to go in and input all of the net forces about like how the planet, ship, and black hole all interact with each other. And then once we do that, we have to guess and check different velocities that we think, and then keep running the program until the ship does no longer crash. So I found that it didn't crash if the initial velocity is negative 4.5 e to the 7, 2.3 e to the 6, and then 0. And then during that, after 30 minutes, the ship was 8.8 x 10 to the 10 meters away from the black hole. So some sources of error is that it was trial and error, so we found the initial velocity, so it might not be the most accurate, or not the best option, but it still works. And then since it's simulation, we don't account for all the forces and variables that could be present in the real world, so it isn't an 100% accurate representation. So in order for the spaceship to completely orbit the black hole and not leave the orbit, but also not crash into the black hole, I found that the initial velocity has to be negative 4 e to the 6 in the x direction and 9.6 e to the 6 in the y direction. And I found this through a lot of guess and check. But as you can see in the picture, they both orbit the black hole without crashing into it. And then the difference between the net force and rate of change of momentum is that the parallel and perpendicular components of net force and rate of change of momentum correspond to the change of object, speed, and direction, but the net force causes a change in momentum. Its parallel component changes the speed and perpendicular component changes the direction. And then the rate of change of momentum is the result of the net force of an object. So the parallel component changes the magnitude of momentum, and the perpendicular component direction of the momentum changes direction of the momentum and direction of velocity. Thank you so much.